Good morning. Today we are going to study acidity and basicity of organic molecules. This is vast and confusing topic for most of the students, if I could say, even to teachers. Certainly, it depends extensively on experiments, different conditions, but still, when the question comes, how to deal with questions as far as our 12th level exams, that is NEET, JEE Mains, and JEE Advanced, are concerned. So, today our focus will be mainly understanding the basic concepts of acidity basicity plus understanding the approach towards solving the questions if we have to face such questions in coming exams. For that, we'll definitely go through the past questions that appeared in JEE Advanced in recent past. Okay, so let's start today's work, that is acidity and basicity. So acidity and basicity of organic molecules, to explain acidity and basicity, there are several theories proposed in general in chemistry. Because acidity basicity is not a particular property limited only to organic chemistry. It is applicable to all physical chemistry, certainly in organic chemistry as well as organic chemistry. So, only one approach, one theory cannot explain all the behaviors, all the possibilities of acidity and basicity of different molecules. There are several theories. Few to name are Arrhenius concept, Laurie Bronsted. A very important one certainly is Laurie Bronsted. Second most important for us is the Lewis concept of acidity and basicity. Then in organic, we definitely need some idea of solvent effect or solvent concept of acidity basicity. Then on rare occasions, to explain certain observations, we do use hard and soft acid base concepts also. So there are so many theories available in acidity and basicity of organic molecules, or in general all the molecules. As I just named, I'll just write Arrhenius, Laurie Bronsted. Laurie Bronsted is the most important for us. Then there was Lewis. Then I said solvent theory. After solvent theory, there is HSAB concepts, etc. So there might be various concepts. In our limited time, there is no need for us to revise all these concepts as such. But certainly, what we need to know is a particularly important concept for us, that is Laurie Bronsted concept. Now, Laurie Bronsted concept is a protic concept. LNB concept is a protic concept. As per it, the acid is a proton donor and a base is a proton acceptor. That is the basic thing. Then Laurie Bronsted also gave a conjugate acid base pair concept. They gave a concept of conjugate acid and base pair. To brief this concept, I would simply say that if a molecule is acting as an acid, then there are always two species at a difference of 1 H plus. So the one which is having that extra H plus is called conjugate acid of a pair, and the one which is not having or is having a less H plus by 1 is called the conjugate base in that pair. So conjugate acid base pair. Okay. In this particular thing, there is an important conclusion that in a conjugate acid base pair, if acid is found to be a stronger acid, then the base will be relatively a weaker base. If base is behaving as a stronger base, then acid is going to be a relatively weaker acid. Okay, this conjugate acid base concept and then the pK values extensively uses water as a base solvent. Okay, so first let us understand what is the pKa of water. What is the pKa of water? If water is acting as an acid, then I can write its equilibrium like this. Water as a liquid which will act as a proton donor. This is the solvent forming H3O plus and OH minus. Now, as this water molecule is acting as a solvent, so its concentration will be taken as constant. Ka of water can then be written as H3O plus concentration multiplied by OH minus concentration upon the concentration of water. Solving this, we come to pKa of water is 15.74. Okay, so pKa of water is 15.74 and Ka of water is 1.8 into 10 to the minus 16, which makes it certainly a very weak acid. It is quite a weak acid. Okay, you can see its forward equilibrium constant as an acid is 1.8 into 10 to the minus 16 when I'm talking about its autoionization. Now, how do we calculate the PKB of water? Okay, so for PKB of water, I can say OH minus is acting as a base. Solvent is water. Doing the same process again. When this will accept H plus from this solvent, it is forming H2O and releasing OH minus. If I'll write the equation, this is constant. OH minus and OH minus concentration will get cancelled. And Kb of this water is coming directly equal to the concentration of the water, which is 1000 by 18 or 55.56. So PKB solving this is coming to 1.74 minus 1.74. See, minus 1.74. So that makes OH minus to be a quite strong base. Okay, that makes water to be a OH minus to be a strong base. Now, if we understood what is this Ka and Kb, next point I want to tell you is whether a reaction will go in a forward direction or not. If I want to predict this particular property in a chemical reaction, how will I proceed? For that, let me take again in continuation example of water. This particular thing will be applicable for further acids also. But starting as water, universal solvent, most commonly used solvent, let's proceed that. If I have an acid HA, okay, I add it in water and use it as H3O plus and A minus. I want to see whether this water will act as a base and this HA will act as an acid in this water or not. So this equilibrium will be established. I want to know whether the K equilibrium of this is going to be greater than 1 or less than 1. That is, whether this equilibrium will proceed forward or will go backward. So K equilibrium of this reaction can be written as H3O plus into A minus concentration upon HA and H2O. Is it okay? So if I take this whole concentration replaced in terms of Ka of water and Ka of HA, I also used Ka of H3O plus, which is just reverse of, oops, kb of water. So I'll end up to K equilibrium is Ka of Ha upon Ka of H3O plus. Okay, and I can write P equilibrium is Pk of Ha minus pKa of H3O plus. I don't know this value. I'll just put it as some x. Okay, as far as this value comes on solving negative, as far as this value comes negative after solving this pk equilibrium, if is coming negative, then k equilibrium will definitely be positive. That is, it is greater than 1. Okay, it will have a positive power. It will have a positive power, so it will be greater than 1. That means, what does it mean? That if Ka of Ha is greater than Ka of H3O plus, then this equilibrium will move forward. Okay, that is, if Ha is acting as a stronger acid over H3O plus, then equilibrium is moving forward. Now, what I just said, there is a conclusion related to what I just said. Acids with a lower pK value than minus 1.74 will protonate water completely. Remember this. All acids which will have pK value lower than minus 1.74 will protonate water completely. Similarly, all bases whose conjugate acid, whose conjugate acid will have a pKa higher than 15.74. Conjugate acid should have a pKa higher than 15.74, will deprotonate completely. Okay, will deprotonate water completely. That is, they will abstract H plus from water completely. Correct? So this is how the chemistry of acidity and basicity can be related for other similar acids also. We have just taken water. But for other acids also, we can write a similar type of equilibrium. We can calculate their Kas. We can calculate their Kbs if they are amphoteric, or Kbs of the conjugate base if required. Correct? Using that concept, we can further predict the reactions of different organic acids like alcohols, phenols, carboxylic acids, amides, etc. in a given solvent in a given equilibrium. Now, see, ionization of an acid is certainly very much influenced by solvent. Okay, it is very much influenced by solvent. Now, how does a solvent have impact on the ionization of an acid? Well, solvent has an impact. For example, let me take an example. If I take HCl under aqueous conditions, then see, for this particular equilibrium of ionization as an acid, H plus and Cl minus being formed, delta G of reaction is found to be minus 40. Okay, if delta G of this reaction is found to be minus 40, certainly this equilibrium, K equilibrium, okay, on solving the value of the K equilibrium, this is going to be dominant in forward direction. K equilibrium will be much greater than 1. This reaction is going to be dominant in forward direction. Okay, because you can see delta G free energy change of this reaction under aqueous conditions is minus 40. Negative delta G indicates the spontaneity of this reaction. More and more negative it gets, more and more faster, more and more spontaneous the reaction gets in that particular direction. Is it okay? If I take same reaction under gaseous conditions, that HCl as a gas is undergoing an ionization as H plus gas and Cl minus gas. Then look at the free energy change delta G standard at 298 Kelvin only. For gaseous ionization of HCl is plus 1347 kilojoules per mole. Not only positive, but is largely positive. Okay, so this particular value, this is indicating that this K equilibrium is going to be very, very less than 1. This is going to be very small. Okay, so what practically is, I can make you a feel that what does this value indicates? What is the conclusion? Solving this, if I find K equilibrium for this reaction, okay, solving this, if I want to find K equilibrium for the reaction, I can say I will get somewhat like one molecule out of 10 raised to power 240. One molecule out of 10 raised to power 240 molecules of HCl will undergo dissociation. Will undergo this dissociation. So you can get a feel that this is almost a useless reaction for me. Like I cannot ionize HCl like this as an acid in gaseous condition. So this is not possible. Next, if I want to say what is so special about H plus. Okay, what is so special about H plus? If I want to say if at all an H plus is there in gaseous state and it accepts H3O plus in gaseous state and forming like this, then its delta G standard is found to be minus 686 kilojoules per mole. Minus 686. So just imagine that this H plus will always exist as H3O plus rather than H plus, or will undergo dissociation forming a free cation, proton. So what I want to prove, an isolated proton, if there is any, is incredibly reactive, is too reactive to handle. It always binds itself with some neutral molecule and would like to exist as covalently bonded. Otherwise, H plus, isolated H plus in gaseous state is like a traveling proton, which is very, very unstable. So, what is so special about H3O plus? It is still charged. It is still charged. So, H plus, if is unstable, then H3O plus is not unstable. Well, H3O plus is still having a complete octet. It is not having an incomplete octet of any of the atoms available. So it is relatively more stable as compared to H plus. And if I talk about H3O plus under aqueous conditions, then what not? It is so very stabilized by the H bonding given by solvent. Correct? So, how H bonding is given by solvent? This is my H3O plus, a tetrahedron molecule. These are the other water molecules present in the vicinity. and these are the H bonds which will stabilize my hydronium ion under aqueous conditions. So from this you can imagine that under aqueous condition H3O plus is further more stabilized, is even more stable. Okay, so it is even more stabilized under aqueous conditions. To conclude the discussion so far, that what all factors are affecting the acidic strength of a particular organic molecule. I would say there are a number of factors that could affect the strength of an acid, but the main three factors which are deciding factors or which decide whether a particular compound will act as a good acid or not. First is stability of a conjugate acid. Here, this is conjugate acid, this is conjugate base. Sorry, stability of the conjugate base. So, this is the conjugate base. As this conjugate base will become more and more stable, it will be less attracted towards H plus, thereby diminishing the backward equilibrium and supporting the forward direction of this equilibrium. So, as the stability of this A minus, the conjugate base, is increased. Now, the point is the stability of this conjugate base will depend on what all factors. So, I will say stability of negative charge, stability of negative charge density. If it is, if the stability of conjugate base will be if there is high charge density on A minus. Electronegativity of A directly increases stability of A minus. Electron withdrawing groups in the molecule directly increases the stability of A minus. Now, when I say electron withdrawing groups, then I include minus H, minus I, minus R. Whichever way they delocalize that negative polarity, they increase the stability of the conjugate base. Okay? Hybridization. Hybridization of A in A minus. Okay? So, stability will certainly be directly proportional to percentage of S in hybrid orbitals. So, if this negative charge would have been on sp, it would be better than sp2, then comes the sp3. Correct? Point number 2 is bond strength of HA. Now, why do I want about the bond strength of HA? Well, when I talk about this equilibrium, I'm not writing everything like, but still I need to write solvent, solvent, solvent. So if I take this reaction forward, I have to break HA bond. Okay, and equilibrium is controlled fundamentally by delta G. Delta G involves the free energy of the product as well as reactants. Okay, and delta G certainly depends on delta G is equal to delta H minus T delta S. Delta H. This delta H involves the solvation of H plus, solvation or stability of A minus, and the stability or the bond dissociation energy of HA. So, easier this bond to be broken, faster the reaction in the forward direction. I can say the Ka of HA is inversely proportional to bond strength of HA. As soon as this bond strength decreases, Ka will increase. And we have such a good example for this. As you remember, HF, HCl, HBr, HI. This is the order of Ka. In inorganic, you might have done this or you will do it in the near future. That HI being the weakest bond will be acting overall as the strongest acid. HF is relatively a weaker one. Next factor, as I said, will certainly be the solvent. We have already seen the solvent effect when I talked about HCl ionization under aqueous condition and under gaseous condition. Okay, but one extra factor that I would like to add here that okay, I'm taking everything in a liquid phase, I'm taking everything in a solvated condition. But what about this A minus solvated? As and as this A minus becomes more and more stable by the solvation support from the solvent, this equilibrium can be pushed forward. Okay, but there is one more important factor related to solvent. Okay, the choice of solvent limits the pK range we can use in a particular medium. What I'm saying that the choice that whichever solvent you want to use, you select. The choice of solvent limits the pKa range we can use. What do I mean by that? For example, if I talk about water, in water, our effective pK range is minus 1.74 to plus 15.74. Okay, minus 1.74 to plus 15.74. Now, what happens if I take something which is more acidic, okay, more acidic than water? I can have the strongest acid in a water is H3O plus, and the strongest base in a water which can exist is OH minus. This is my range. That is it. Okay. If anything extra, if anything stronger than H3O plus is introduced in the medium, it will start making water. Okay. It will start making water as a base. If I introduce a base which is stronger than OH minus, then it will start making water as an acid. But my overall range is only this. Overall range is only this. I can use anything within this range, but not beyond, and this is called leveling effect. This is called leveling effect. Okay? Even if I want to remove proton from something which is having a higher pK, if I want to remove proton and I want to add it in water, I have added it in water and I want to remove proton from it. Let me take example of acetylene which has pKa of 25. Now I want acetylene to behave as an acid in water. So what will I do? I'll write that I want a reaction like this, that C minus and H3O plus should take place. Correct? Now here, this in first pair of conjugate acid base, I will write this is the conjugate acid 1. This is the conjugate base 1 in a pair 1. This is the conjugate acid 2 and this is my conjugate base 2. Correct? Now, what I want is that to make this equilibrium forward, pKa of CH triple bond CH, that is acetylene, should be less than minus 1.74. Correct? Then only this will go forward. But it is not so. So this equilibrium is pushed totally backward. I cannot make it forward at all, because for this equilibrium to be forward, Ka of acetylene upon Ka of H3O plus, that value, that K equilibrium should be high, should be greater than 1, which is not the case. So this reaction will not take place. This reaction will fail in water. I hope I have made my point to a certain extent. Now, if I want to change the solvent, let me try another solvent. So here I have introduced NaNH2 and we have used solvent for this particular. I would write it was like this. Okay, equilibrium we can never say either of the direction is becoming 0. Let me take ammonia as a solvent as an NH2, otherwise is a solid. Okay, so we have added acetylene in ammonia and NH2 dissolved in ammonia. Now, as I've already told, pK of this is 25. Here the equilibrium will be like this. This is our conjugate acid 1, this is our conjugate base 1, this is our conjugate acid 2nd, this is our conjugate base 2nd. This pK is 25 and the pKa of ammonia as an acid is 33. Okay, so if I want to predict what will be the K equilibrium of this reaction, it is K of acetylene upon Ka of ammonia. pK values I have, so I'll write it is going to be 10 to the power minus 25 upon 10 to the power minus 33. Correct? If I solve this, I think I'll get 10 to the power 8. So this clearly indicates the value of K equilibrium, clearly indicates the ease of this deprotonation of acetylene when it is dissolved with NaNH2 in ammonia. And here it is just opposite. Here it is just opposite. This equilibrium will go in the backward direction. So the use of solvent that we are going to use for understanding, for studying a particular acid-base equilibrium is a very crucial choice for a reaction to happen, for a reaction to be observed. So whenever you select a solvent, of course, you cannot remember all these things. We'll go to use of electronic effects just in a few moments and start predicting the acid-base strengths. But this is how you need to practice. You need to write in a chemical equilibrium reaction given the conjugate acid-base pairs. Then you have to compare a conjugate acid A first versus second, or a conjugate base 1 versus 2. A very handy rule that I would like to share with you, always as a rule, equilibrium always shifts from strong acid base to weak acid base. Okay, so you can see relatively this is the stronger acid, this is the weaker acid. So always as a rule it moves from stronger acid base pair to weaker acid base side. Okay, take it as a rule, it will help you. Based on this, This was one of the questions which appeared in J 2003. To have a clear view, let me enlarge it a little. Now, the question was based that if in this particular structure only 2 moles of NNH2 are given, then what will be the structure of an ion? As I think through ionic equilibrium, all of you know that order of reactivity, order of reactivity will be same as Ka. So the one which is going to be strongest acid will react fastest and then the others. First, because this is going to be COO minus carboxylic acid. Then I have two phenols. Okay, I have two phenols, but this phenol has an electron withdrawing support from this NO2, whereas this does not. Correct? So this has more delocalization. So this will be our acidic site number second order. Okay. Then I have phenol versus acetylene. This is ultimately going to be sp hybridized C minus, whereas this is going to be O minus. We have seen the conjugate base. More electronegative minus is more stable. So this is going to be third and this is going to be fourth. So if I give first mole of NNH2, the first site of deprotonation is this H plus. Second mole of NH2 will deprotonate this site. If they would have given third and fourth, then the others would have been taken in um, this acid base equilibrium. But here, okay, but here it is not so. So let us check. Here CO minus and O minus, others are maintained intact. Here CO minus and C minus, no, not possible. C minus, here the group is totally gone, and these are the two phenols, not possible. Answer should be A, and it was given A. So whenever they ask, you should decrease more as you should react in the decreasing order of their acidity. Higher the Ka, faster will be its acid base reactions. Now, till now, we have been discussing general acidic general factors affecting all types of acid. Now, let us come to organic acids. In case of organic acids, the first is alcohols. In case of alcohols, this is our dissociation constants. Correct? If I compare them with water, I think all of you can understand that this H is having no inductivity as the reference. R is a plus I effect. So if I talk stability of conjugate base, then HO minus will be more stable than RO minus. So in general, I can say water will be stronger acid than alcohols. Okay, in general, let me write this. Except methanol, the final order which has been observed was methanol is slightly stronger than water and then the other alcohols. Okay, not much of the reasons are relevant or are even known when I talk about methanol. Now, this particular order is taken either when they are dissolved in water or in absence of any other solvent, there is a direct acid base reaction between the species. Then this order is valid. I need to specify my comment because, as I have just told you, that solvent can change any order of acidity basicity here and there. So certainly, if solvents will be changed, there could be effect on acidic basic strength or order. Yes, there will be. Okay, so this is how alcohols can act as acids. Yes, one more thing I would like to add here. As I introduce electron withdrawing groups, as I introduce electron withdrawing groups in these alcohols, it will definitely become more and more stronger acid. Okay, so all I can say is CH3 CH2OH will be weaker acid than CH2 ClCH2OH will be certainly weaker acid than CCl3CH2OH. This is what I want to intend. Okay, next we go to phenols. Now, in case of phenols have OH attached to electronegative benzene, or I can say is attached to sp2 carbon. sp2 carbon will definitely be more electronegative than sp3 carbon. When I form this anion, it is also resonance stabilized. If it is resonance stabilized, certainly this is going to be a stable conjugate base. So now I can conclude the Ka of phenol will be highest, then it will be methanol, whatever we have studied till now, then it will be water, and then there will be other alcohols. Correct? And in case of phenols also, again I will say, in case of phenols also, if I'll introduce certain groups, so if this G is electron withdrawing groups, Ka of phenol will increase, and if this G is electron releasing groups, Ka of phenol will decrease. Okay, so Ka of phenol will keep on changing based on presence of other groups. Here, Ka of phenol is pKa of phenol is 9.95, 15.74. Okay, 15.74 is for water. If I talk about methanol, it is 15.2. Correct? And for ethanol and others, I will just abruptly mention as 16.5, somewhere like 16.5 key zones. Okay, it is still, I'm just saying a zone. Rather, I should write, because 1 degree, 2 degree, 3 degree variations will be there, 16 to 17. That is better. So you can see how it changes. In case of phenol, one important factor that we take care when a group is introduced is the H bonding effect of H bonding in case of phenols. Well, H bonding can affect always. Let us compare acidity of phenol versus acidity of orthonitrophenol, metanitrophenol, and paranitrophenol. Now we know that NO2 group NO2 group is a strong minus R and minus I group. So it is overall a good electron withdrawing group. It will increase the acidity of phenol. When we compare and when we draw and compare the conjugate base stabilities, then certainly this is our reference molecule. No extra effect, no extra supporting factor is there. In this case, yes, I will get support of resonance of NO2 to stabilize O minus. But when I was ionizing this, I had to overcome this H bond. So this makes my delta G a relatively less negative than expected. When I ionize this, then I can use only minus I effect of NO2. I cannot use its resonance effect as it is a metaposition. Correct? So, using minus R and minus I only, no H bonding, I can say the Ka orders should be ortho, para, because from here I can use its minus R, and minus I is also effective as it is closer to O minus. Para I can use minus R, but distance increase, minus I decreased. Then in meta at least I have minus I, and in PHOH I have nothing. Okay, but due to H bonding, final Ka orders will be para, ortho, meta, PHOH. Okay, final orders will be this. Remember, H bonding has certainly decreased the K of our acid, but the overall decrement will be only between para and ortho. Okay, the destabilizing or the decrease in my forward K equilibrium due to this intramolecular H bonding will not or will never dominate over the stabilizing phenomena that NO2 brings from ortho and para position. It will never dominate over that. And that is why, despite this intramolecular H bonding, my ortho will not become weaker acid than even my meta substituted. Okay, so how to handle H bonding in phenols? Be careful. Just if there is an intramolecular H bonding in reactant side and you want to decrease the Ka, then you should just jumble or shuffle within the set which has the same resonance, not abruptly here and there. Correct? Yes, edge bonding has certain other examples, certain other places also where it can play a very important role, not in phenols, but I'm taking another example is you might be aware of Ka1 of maleic acid is more than fumaric acid. Okay, Ka1 of maleic acid is more than that of fumaric acid. But Ka2 of maleic acid is much less than that of fumaric acid. Now let me explain why. Maleic acid is C double bond C, COOH, COOH. Okay, this is my maleic acid. So, in my maleic acid, there is H bonding here. Correct? When I do my first ionization, I'll ionize this H plus, which is not a participant of H plus H bonding. And now let me write. So COOH, COO, del minus H bonding. So there is increase in H bond strength. There was H bond before also. There is H bond after also, but there is increase in the strength. This was for my Ka1. If I now compare for Ka2 and I want now this H plus to be removed. So if I want to remove this H plus now, this time when I will do the same thing, this is becoming del minus del minus. This was already del minus del minus. There is no H bonding in conjugate base. There is no intramolecular H bonding in conjugate base. And to add to that, there is repulsion because rotation is restricted. There is repulsion in 2COO minus. As a result, this is becoming unstable. If I talk about fumaric acid, there was no H bonding beforehand. As you all know, for H bond, you need H attached to fluorine, oxygen, and nitrogen, not to carbon. So there was no H bonding before. There will be no such H bonding in forward, in second dissociation. But in second dissociation, when you will draw, the 2CO minus will at least be in the opposite direction, will be far away as compared to my malic acid second conjugate base. So this will be more stable. And thus, from weaker to stronger H bonding, there is Ka. This is a supporting factor why Ka1 for maleic is more than fumaric. But from H bonding to no H bonding and repulsion, it decreases the second dissociation constant of malic as compared to fumaric. Correct? Let us go through one more question. This acid-base reaction equilibrium also help us to purify, to identify, and to have some test for different organic molecules. Let us have one example. Among the following, the total number of compounds soluble in NaOH. Now, for these compounds, whichever they are being taken, if I take them as HA and I'm taking a reaction with NaOH, so our target is water should be formed and NaA minus should be formed. If I take this as my conjugate acid 1, then it's conjugate base 1, then conjugate acid 2, and OH minus is my conjugate base 2. So what I want overall here is my conjugate acid 1, that these acids should have had a greater than Ka greater than 15.74 or pKa less than 15.74. Okay, aniline, no question, possibly nahi. It is having no acidic H even. Benzoic acid. Benzoic acid certainly is possible because it has pKa of 4.20. Correct. Now here it is an alcohol, it is not a phenol. Alcohol, as I already told you, will have somewhere around 16. Its pK is going to be 16. So this cannot undergo that dissociation. Phenol will have pK of 9.95. So this will make the equilibrium forward. Solubility will come when this salt will be formed. These compounds are not water soluble. These salts when formed, okay, these are the reason for soluble in NaOH. When they are formed, then our compound will be soluble in NaOH. Okay, so NO2, no choice. Phenol, yes, despite that there is a plus R group, still it will not decrease to the level that its pKa will become less than 15.74. So it is continued. No. Overall, it is an acid. Yes. So 1, 2, 3, 4. 4 will go to form this type of soluble salt, and so 4 will dissolve in NaOH. Okay, this question appeared in JE in the year 2010. Okay, on this particular similar concept. Let's move to carboxylic acid. I think carboxylic acids are very good acids. All of you are aware that when they ionize, they generate very stable conjugate base which has two equivalent resonating structure. So they are very stable conjugate base. They are very strong acids. In general, their pKa ranges somewhere around 4.76, 4.75 around, and is further increased. Okay, this pKa is, this Ka is further increased if there is a presence of electron withdrawing groups. Okay, if there is presence of electron withdrawing groups in this R, okay, presence of electron withdrawing groups in R further make them stronger acids. Okay, they'll become still more stronger acids. Just to exemplify, CF3COH pK is 0.23. You can see less than 1. It is such a strong acid. Okay, acetic acid I told you 4.75. This is 0.23 and so on. Okay, so if you introduce electron withdrawing groups, their acidity will increase. In case of benzoic acid, similar effects, similar thing, but a particular ortho effect is observed in case of benzoic acid. What does it say? It says that irrespective of electron releasing or electron withdrawing effect of G, if there is any group present at ortho position in benzoic acid, okay, it will always make them stronger acid than parent benzoic acid. Correct? Even if this G is EWG or electron releasing group, always as a rule, if there is any group present at ortho position to COOH, then it increases its acidity as compared to COH. If you have more of such choices, the basic reason for this is steric. Presence of G at this position pushes COOH out of the plane with the ring. As a result, when it is pushed out of the plane, the plus R effect of ring is diminished, and thereby it becomes even stronger acid than benzoic acid. Okay. Now I'm writing a one particular point. Always remember, overall order of acidity in case of carboxylic acid is formic acid is strongest, then is the benzoic acid, and then the other aliphatic acid. Okay, benzoic acid has a pKa of 4.2, aliphatic have 4.7. Okay, aliphatic acids will have pKa of 4.7. Formic acid has further methanoic acid, that is further less pKa value. Okay, moving on. The compound that does not liberate CO2 on treatment with aqueous sodium bicarbonate solution. Now, how this CO2 is liberated? What happens if some acid is made to react with NaHCO3? Then a possible reaction is formation of NaA plus H2CO3. H2CO3 being unstable will release CO2. So basically, when they ask whether this CO2 will be released or not, the basic question is still the same, that which of them will react with NaHCO3 and make the equilibrium forward towards H2CO3. Okay, I have written the value of H2CO3. First pK1 is 6.35, second is 10.33. But as we are asked to react with bicarbonate, so we have to use the pKa 6.33 for comparison. Okay, so anything that will have uh, lesser pKa than 6.35 will make the reaction forward. Benzoic acid, I have already told you, has 4.2, so this will make the reaction forward. Not the answer. Benzene sulfonic acid is even stronger acid. No. Salicylic acid is COH. Carbolic acid is phenol. So its pK is 9.95, less than this. So it will not make the reaction forward, and thus reaction will not take place, or CO2 will not be liberated. But a very important thing you need to remember, that what I just said, that when you want phenol plus NaHCO3, okay, the equilibrium is like this. You cannot have PHONA plus H2CO3. That is true. But when you have phenol plus Na2CO3 and you want to go phenoxide plus NaHCO3, then this reaction will be forward. Correct? Because the second dissociation constant of H2CO3 is 10.33 and phenol is 9.95. 10.33 pK 9.95. Okay, so this is a less pK, more Ka, making the equilibrium forward. So please remember, phenol do not react with H2CO, NaHCO3, but it does to one step up to NaHCO3 with Na2CO3. Okay, the correct order of acidity, and I think you can handle that question easily. Let us move to some other cases like hydrocarbons and nitrogen acids. Well, this particular example I wanted to share particularly, okay, in case of hydrocarbons. Hydrocarbons, whatever in the world becomes the stabilizing factors for hydrocarbons conjugate acid, they still will continue, please mind it, continue to be weaker acids as compared to any oxy acid, any acid which releases its proton from oxygen. Okay, now why I wanted to say this, see, in all these examples, when I remove the H, which they have marked very clearly, there will be generation of aromaticity in this 5-member ring sector. Correct? So we expect that, yes, certainly this is going to be a very, very strong acid. Okay, we may expect that this is going to be a strong acid. Similarly, in this series, I want to just add that if I take cyclopentadiene, then becoming cyclopentadienyl ion, its pKa is 16. Okay, see, it is still not stronger than water. It is, if even if you go to compare, even if you have to compare to alcohols, please take it as a relatively weaker than the usual ones. Now let me take these. So aromaticity is coming. This is going to be the best acid. Why? Because this is a rigid structure, it will have a complete resonance in all the 3 rings. Here, only 2 rings, okay? But along with that, I can have this extra ring resonance. But this is this can rotate. So it is not going to be as effective resonance as this one. Okay, so you can see that 3 rings, but this is rigid. It can have more rigidity towards the planar structure. Okay, here it is not. Okay, whereas here, when it comes, the whole system is planar, but the resonance is only with respect to rings. I think taking this into consideration, you will be able to conclude that the correct order of their acidic strength will be R, then it will be Q, then it will be P. Okay. Moving next. Today we'll have a little longer lecture because the topic is quite extensive. Basicity. Basicity, now we want to say that what do we mean by basicity? That there is this something which can donate a lone pair, or I can say accept a proton, and forming HP and OH minus. This is what we want to say about basicity. Now, the factors which affect the basic strength of a particular organic base first is the ease of lone pair availability, and then the ease of its donation on a particular base molecule. First, is it available or not? Why it won't be available? For that availability, we'll think whether it is delocalized, delocalized lone pair, basicity will go down. Okay, lone pair on electronegative atoms, basicity will go down. Correct? Lone pair on high percentage S hybrid atoms, basicity go down. I hope I have made my point that if the lone pair is easily available, then definitely it would be easier to donate it and make a molecule more basic. Here I would also add one factor called flipping. Flipping in amines. Okay. N- uh, Ammonia has a flipping tendency of somewhere 10 to the power 21 times per second. What do I mean by flip? This will become exactly upside down inverted structure like this. Okay, as a result of this flipping, basicity goes down. Basicity goes down. So, if somewhere flipping can be stopped, then certainly the basicity increment will be observed immediately. Okay. Factor number two is stability of conjugate acid. Now, this time our conjugate acid is positively charged. So, electron releasing groups will increase the stability of conjugate acid. As it become more stable, equilibrium will go forward. This part is very much like our basic acids factor only. Correct? Then let us start with the organic bases. First is amines. Now, in case of amines, RNH2 when takes H plus, okay, it forms RNH3 plus. R2NH when takes H plus, it forms R2NH2 plus. R3N when takes H plus, it forms R3NH plus. Correct? So these are the different types of amines. Okay? Now these equilibriums will be influenced by definitely the lone pair availability here, which will be increased with the presence of alkyl groups, and the hydrogen bonding if there is any of these conjugate acids form. Okay, or I can simply say there are lone pair availability on amines is 3 degree greater than, sorry, will decide. Okay, and conjugate acid stability will decide order of basic strength. Okay. Now, conjugate acid stability depends on two factors. First is plus I. Using plus I can say 3-degree conjugate acid is most stable, then 2-degree conjugate acid, then the 1-degree one's conjugate acid. Okay? There is one more factor. H bond with solvent. If it is there, then definitely solvation will increase the stability of conjugate acid. So, for that, 1-degree conjugate acid is more stable, then 2-degree conjugate acid, and then will be the 3-degree conjugate acid. Now, these are two contradictory orders. Now, total dependence is an experiment. 2-degree is always best. 2-degree, no issue. 2-degree, whichever dominates. Okay. Final order, if plus I dominates, then 2-degree, then if plus I factor is dominating, then it will be 3-degree, and then it will be 1-degree. If H bond dominates, then it should be 2-degree, then 1-degree, and then it should be 3-degree. Okay. In case of methyl, if R is methyl, then see methyl is small. So there is less plus I. As its hydrophobic part is small, H bond will become effective. H bonds will become dominating. And so order is 2-degree, that is Me2NH is a better base than MENH2, and then it is Me3N. See, 2-degree, then 1-degree, then 3-degree. If R is ethyl, then hydrophobic part is increased. Okay. Here H bond dominated. Here plus I is better and H bond less. So order is Et2NH, then it is Et3N, and then it is ETNH2. Okay, ETNH2. Now, if you see this Et2NH, Et3N, and ETNH2, correct? I can say 2-degree, then it is 3-degree, then it is 1-degree. In all the cases, remember ammonia is the last. Okay? To memorize, what I would suggest, see, methyl is smaller, na? So 213, smaller value, 213. Ethyl is the bigger alkyl, bigger value, 231. And this whole thing was only in aqueous conditions when solvation. So this whole thing was under aqueous conditions when the solvation factor was there. In gaseous condition, when there is no such solvation, then there is no problem. Always the order is 3-degree greater than 2-degree greater than 1-degree for all amines, irrespective of different types. Okay, so this is all about amines. As I told you, flipping can affect quinacridine. In this quinacridine, the nitrogen is present at bridgehead. In Et3N, the nitrogen is present like this. Flipping can take place. Quinacridine. These are here the pKh, that is conjugate acid Kas are given. Kb is directly proportional to pKa of conjugate acids. Okay, are directly proportional to pKa of conjugate acids. So this is stronger base than this one because no flipping. Use this no flipping factor only when other factors are constant, that is inductive resonance are constant, otherwise they are more important. If I compare amides versus emides, then I think you can see here my nitrogen lone pair is delocalized to 2 oxygen, only to 1 oxygen. Well, I must tell protonation in amides is at oxygen. So here this entire lone pair is coming to this oxygen. Here it is distributed to 2. Certainly, which is going to be a stronger base? Amides. Okay, but still poor than amines because there is no delocalization of lone pair as such in amines compared to amides. Pyrrole, aniline, and pyridine is a very important example. See, pyrrole. If I protonate this lone pair of pyrrole, I will lose aromaticity of pyrrole totally. Okay? If I lose the aromaticity, certainly this equilibrium will be pushed towards backward direction. Certainly this equilibrium will be pushed towards backward direction because from aromatic to non-aromatic, structure is becoming unstable. In pyridine, even when I'm having this protonation, this was aromatic, this is aromatic. No effect. Correct? And is having a resonance stabilization of this N plus. And resonance stabilization of N plus. Aromatic. But N plus cannot resonate. Okay? In fact, this is a minus I group. This was aromatic. And this is becoming non-aromatic. So from here we can conclude, okay, that pyridine is going to be strongest base, then it is going to be aniline, and pyrrole is going to be the weakest base of all. Okay, this is a very important point. Please go through it. I'll write guanidine. Guanidine is NH2, C double bond NH, NH2. Amidine is R, C double bond NH, single bond NH2, and amides. Take the order of KB is like this. Why? If you'll donate proton to these, it will be the sp2 centers. These will take the proton. This is totally out of the race because oxygen is the donor atom, more electronegative. Bad it is. Okay, here when you will form the conjugate, you will have two equivalent resonating structures. Okay, you can compare it with RCO minus type stability. Whereas when you will form this, then you will have three equivalent resonating structures. So guanidines are very strong base, unexpectedly strong organic base. Okay. On this guanidine amidine thing, in 2017, this question appeared. Okay. Among these, certainly 4 is going to be the strongest of all, as I have just told you. Then it is amidine. So 4 and then it should be 2. If you know it just this much, you could have ticked option B. Okay. Just this much ही हमें आता हो कि first it has, sorry, B नहीं, C, that if 4 is strongest and then it should be 1, then you could have ticked this. Because maximum number of students had trouble in second and third only, not in 4 and 1. So by doing this only, you can analyze and you can get the answer. Between 2 and 3, the presence of sp2 carbons will decrease the stability of conjugate. Presence of sp3 carbons will increase the stability of conjugate. For your further reference, I have put this over here. Please go through it. It will help you to understand how the conjugates will behave. I have even used comparison with pyridine. If required, please add it. In case of anilines, there is again similar behavior, but there is SIP. It says presence of any group at ortho position decreases KB of anilines, then PHNH2. Okay, decreases KB of molecule, then this. Similar factors, steric, except in G if is OH and OMe. Okay, these are the only two exceptions where ortho effect in aniline doesn't work. In case when G is PHOH, okay, when it is PHOH and when the group is OH and OMe, then ortho effect won't work. And then what will be the orders? For MEOC6H4NH2, para, then hydrogen, that is PHNH2, then ortho, then meta. And for HOC6H4NH2, there is no zero effect of ortho effect in aniline. This ortho effect is also again due to steric. As NH2 itself is a strong, if this G is also very small, NH2 is small, and if this G is also very small, then there is no point of steric hindrance or steric repulsions, and then no ortho effect is observed in case of anilines. Okay, but there is no such exception when we talk like this in case of benzoic acids. Okay, the exception of OH and OMe is only in case of anilines, not in case of benzoic acids. So here we try to sum up important concepts and questions of acidity basicity as much as we could in our concise time. As usual, I'd like to end my lecture with the instructions that read your notes carefully, solve as many questions of acidity basicity as possible, and post your doubts on our Facebook page. If I could, I would really like to help you through that page. Thank you for watching. Now we'll have the another lecture on the coming Monday. Please appear in coming exams sincerely. Thank you, everyone. Use Saturday, Sunday carefully. Invest maximum time in revising. Goodbye.